As always, I welcome you to the IMAG MSM Working Group on Multiscale Modeling of Biopandemics. I appreciate you being here. I appreciate both of our speakers for joining us. That's very kind of you. And I wanted to say, as usual, that the meeting is live streamed and recorded. So it's viewed by a lot more people than necessarily show up in our afternoons. And our speakers have graciously agreed to discuss afterwards if they're good questions. And so we'll go through both of the talks first and then do questions after the talks are finished. As always, Reinhard and myself are available for questions and comments. Jim Sluka and Lorenzo also. The four of us always want to try to do better, so please help us do that. We have our usual communication channels. Please do help us disseminate notifications of the meetings, update the IMAG MSM Wiki page, LinkedIn page, and let people know about the recordings on YouTube. We have more than 100 recordings so far. They deserve to be disseminated. And we do have a Twitter feed. If you tag things MSM viral, that's great. It helps us probably get the word out, especially for recordings in this sort of situation. Are there any announcements this week that we should go over before we get going? We have a digital twin subgroup meeting tomorrow morning at 11 a.m. Eastern Daylight Time. If you expect to be there and you don't have an invitation, let us know and we'll make sure you have it. Los Alamos, Alan Perlson and his group sent an announcement. They have 2 postdoctoral positions open. They're looking for applicants. And I wanted to, they asked me to announce this on their behalf. They are working on a whole variety of viral infections. It's a group of 1, 2, 3, 4 main senior scientists, and something that they wanted us to call attention to was that you have to have gotten a PhD within the past 5 years. So there's a seniority role for these positions. They also wanted to call attention to the fact, which is not in the slide, that the salaries are very good. They can be upwards of $100,000 a year. And so they wanted to make sure that people were aware of this. If you are interested, you can write to Alan Perlson or the others in the team, or apply online at this jobs posting. And I can, once we get started, I can put the links in the chat for anybody who's interested. Were there any other announcements to make? Reinhard, what's the status of your publication? I think you may have said it last week, but it's accepted, right? Or provisionally accepted.
It is accepted. I've submitted the final file, so we should get galley proofs pretty soon.
And there's another publication with Anna that was provisionally accepted as well, related to model sharing and standardization. It's relevant to the working group. So those are 2 more opinion pieces and reviews from the working group in this area. Any other announcements before we get going? No. So with that, we will go forward. We have 2 talks scheduled for next week. April 21st, we still need speakers, so please help us fill it in. As always, you've heard me say it many times, graduate students, postdocs, welcome to talk. You've spoken before, you have something new to talk about, please feel free to come back. You've been working at a subgroup, you have a grant you're thinking about, please do help us fill in our slots. We need somebody for April 21st. We need somebody for May 8th. We do have some people scheduled during the summer, and those will be interesting, but please do help us with suggestions and volunteering yourself and your teammates for speaking. We would very much appreciate that. Please remember to mute your mic when you're not speaking. We're going to hold the questions until after the two presentations. As always, to our speakers, we're grateful to you for speaking. It's hard to say a lot in 20 minutes, but we try to get through both talks in a reasonable time, so there's some time before 4 o'clock, because even though we reserve time till 4:30, some people do have to drop out at 4, so we want to make sure there are at least some questions before 4 o'clock. And I will try to remind people, if the speakers are running over, I may gently nudge you at 15 or 20 minutes to remind you about the time limit. So our first seminar is from Jonas Hue, King's College London, on machine learning, high content image analysis. And I will turn it over to you.
Thank you. Let me just share my screen. All right. Can you guys see this?
Yes.
Thank you. All right. So hi, everyone. Good afternoon, everyone. My name is Jonas, and today I'll be presenting some of the work that I've done alongside myself and Dr. Lorenzo Veschini, who's in the meeting today as well, and our oral pathologist, Dr. Selvam Tavaraj. I'll be presenting on the application of high content image analysis to H&E biopsies in order to predict patient outcomes in HPV positive oropharynx cancers. Just a quick overview of the presentation today. I'll start with an introduction, then describe our workflow, and end off with some potential applications outside of the research project today. Oh. Yeah, so just a bit of background. Human papillomavirus or HPV infection can induce carcinogenesis in the oropharynx through the E6, E7 viral oncoproteins. And in general, these cancers tend to have a favorable outcome compared to their HPV negative counterparts. This makes treatment de-escalation quite enticing in order to try and reduce the side effects of chemo and radiotherapy. And because they do behave and respond so well to treatment, and they behave quite differently to HPV negative cancers, they are now considered as a separate entity under the new classification, the new staging and grading classification. However, a significant number of these patients, about 20% of them, still end up having poor outcomes. And obviously, treatment de-escalation would be contraindicated in this subgroup of patients. So there's also been a lot of research into identifying new potential biomarkers and prognostic features in order to better prognosticate these patients. So our work today had three main aims. The first was to develop an image analysis workflow to quantify the features of these patient biopsies. We then searched for prognostic features that we were able to measure from this workflow, and finally to use these prognostic features to train a machine learning model in order to predict patient outcomes. Our cohort comprised of two groups, patients with favorable outcomes defined as being disease-free at 5 years, and we compared these against an equal number of patients who had either died of the disease or had a recurrence within 5 years. And we obtained 10 images at 100 times magnification from each of these biopsies and ran these images through our workflow. This is an overview of our workflow, and we use several different open source software such as QPath, Fiji, and Cell Profiler. And I'll go into a little bit more detail in a second, but what we aim to do was to go from the raw H&E biopsies into one that was with each individual cell segmented and classified into their various cell types. Once we have this, we can then measure several different features of the biopsy and search for potential prognostic features. So some of the different things we measured were the quantification of immune cells, such as tumour-infiltrating lymphocytes and plasma cells in the stromal component. We also made several measurements of nuclear morphologies, such as the cell shape, their size, how eccentric they are, and we made several textural and granularity values. So before we created this workflow, we had a lot of discussions with our oral pathologists to decide what are some of the more interesting features of the biopsies that we would like to classify, or things that a pathologist would look at. So some of the features that we measured are actually very well-known prognostic features already. For example, tumor-infiltrating lymphocytes, which have been studied in many different cancer types and have showed good prognosis to be a good prognostic indicator in our cancer type as well. Some features we measured were sort of unclear, such as plasma cells. We're not very sure in the literature. Some studies report good outcomes, some report poor prognosis with more plasma cells. And some of them we are completely unsure whether or not they even have any prognostic value. But there were all features that pathologists may be interested in looking at. We then used the prognostic features to train a neural network model in order to predict patient outcomes. So just to go into a bit more detail about the workflow, the first problem we faced was that of stain variation in hematoxylin and eosin stains. So H&E are mainly used for pathologists to make qualitative assessments, to assess the tissue architecture and what sort of cell types there are in the tissue sample in order to come to a diagnosis. They're not really used for any quantitative assessments. So for example, the intensity of the stain doesn't actually correlate to anything. And it just really depends on how the slides were prepared during the preparation process. And here we can see 3 H&E images all looking very different. Some of them are very pale, some of them are a little bit more intense, and the ratio of purple to pink is also different. So to overcome this stain variation, we use a neural network pixel classifier inbuilt in QPath to try and account for paler slides and to allow our images to be run through a sort of one-size-fits-all workflow. The second issue that we faced was that of crowded cells. So the tissue samples are prepared for staining as very thin sections, 5 microns thick. However, this still allows more than one layer of cells to be sort of packed into the same plane. This means that in very closely packed cells, it can be very difficult to draw boundaries between the cells and accurately segment each individual cell because there's some slight overlap. So what we did to overcome this was to use a published pre-trained STARDIS model specifically trained on H&E images that was applied through an ImageJ plugin to help with the crowded cells. STARDIS is specifically good at drawing boundaries between very closely packed cells or objects by using star convex polygons in a convolutional neural network. And we then use the outputs of Fiji and QPath to do some object-based image segmentation in Cell Profiler, where we go from the raw H&E images into individually segmented cells. We can then classify the cells into their various cell types using a round of supervised machine learning in Cell Profiler Analyst, and we attempted to classify the different cell types such as tumor cells, lymphocytes, plasma cells, as well as cell objects such as nucleoli. This example here just shows how we've gone from the raw H&E images into the accurately individually segmented and classified tumor cells. And these images just show some of the other examples, some examples of the other cell types we tried to classify, such as plasma cells outlined in green, tumour-infiltrating lymphocytes, as well as cell objects like nucleoli. And we also, like I mentioned earlier, we also make several different measurements of the tumor. And one of them, just as an example here, is how we measure eccentricity. And you can see more eccentric cells here having higher values as compared to rounder cells having lower values. So once we've measured all these various factors, so some of the things that we measured were like quantifying immune cells. We also did spatial analysis of the tumor cells and measuring the neighbors to figure out how closely packed they are to one another. And we also, like I mentioned earlier, made several different morphological and phenotypic measurements of the tumor cells. We can then do our stats analysis to identify which of these have any potential prognostic significance. This heat map here is an overview of our data. We've identified 28 different prognostic or statistically significant variables. And the blue values represent the blue boxes represent low values, the red boxes represent high values, and you can see a cluster of patients at the top here with low values on the left, high values on the right, and they correspond to a cluster of poor outcome patients, which are labeled in magenta here. The good outcome patients tended to cluster in the middle with high values on the left and low values on the right. And there was an additional sort of cluster of poor outcome patients at the bottom as well, with a bit of a mix of values. And I think this heat map quite nicely illustrates the inter-tumoral heterogeneity between patients, which is a common issue in cancer research, where patients don't tend to sort of behave in the same way, even though like subset of the different subset groups, just there's a lot of variation even within the same group, which makes it very difficult to accurately prognosticate these patients. So this is a summary of some of the prognostic features we identified. So some of the features of patients who had favorable outcomes were that they tended to have more tumor-infiltrating lymphocytes, more plasma cells, rounder and less eccentric tumor nuclei. Their tumor cells tended to be packed closer to one another, and they tended to have more nucleoli with higher textural and granularity values. One of the interesting things that we also identified were that patients who had good outcomes tended to have more homogeneous values. So there was less variance in the data for many of these morphological values. And because we are making lots of measurements at the single cell level, this allows us to analyze our data in a little bit more depth. For example, when we were developing the model and in discussion with our oral pathologists, we actually expected to find a difference in the cell sizes between the two groups. So we expected that patients with poor outcomes would have larger tumor cells, because you would tend to see large tumor nuclei scattered across the biopsy. However, what we realized was that the data suggested there was no significant difference in terms of the average cell size. However, the prognostic feature was in the intra-tumoral heterogeneity of cell sizes. So just to show you an example, this image on the top here comes from a patient with a favorable outcome, and you can see most of the cell sizes are more or less the same, and they have this sort of the same morphology, being quite oval all throughout the biopsy, as compared to the bottom with a patient from a patient with a poor outcome. You can see some of the cell nuclei are really large as compared to some of the others which are really small, and it's this sort of intra-tumoral morphologic heterogeneity that is the prognostic feature. And I think this lines up very nicely with a lot of the current research in head and neck cancer, mostly looking at intratumoral heterogeneity in terms of genetic heterogeneity. And so although we don't do any genetic analysis here, I think it's some of these morphological heterogeneity could potentially be explained by an underlying genetic intratumoral heterogeneity. And next we then use the 28 prognostic variables to train a neural network model with 4 hidden layers, 16, 8, 8, and 4 nodes in each layer respectively. And we did, we split our 567 images into an 80-20 training and test set split. And we evaluated the model, which had an overall accuracy of about 78.76% and some fairly promising sensitivity and specificity values. On the left, bottom left here, as we would expect, there's a very clear split using the model on our training data. And when we apply it to our test set, there is a fairly clear split as well. However, of course, there is room for improvement. We then went on to do a k-fold cross-validation with 10 folds to validate the model, and we see some fairly similar values to that when we applied it to our test set. Just to touch on some of the advantages of our workflow, we use only routine H&E stains without any additional biomarkers. Using additional biomarkers may not always be very feasible in a routine diagnostic pathology service, where the cost of biomarkers may be prohibitive and the additional time required to do additional stains may not be very practical. This also allows us to keep it low cost, of course, because we don't use any additional stains, but also because our workflow uses only free open source software. And we also don't require any whole slide scans. Whole slide scans have been causing quite a bit of barrier to entry for a lot of pathology services, because the cost of buying a slide scanner is quite expensive. And also, if you don't have a slide scanner, currently in the UK, it costs about £45 for us to scan just one slide in. And our workflows also has quite a low computational cost. Each patient was analyzed in under 2 hours with a standard laptop with 8 GB RAM. There's nothing fancy. And this also allows us to keep it time efficient, and which means that it doesn't delay diagnosis and initiation of cancer treatment, where every day and every week that we delay treatment can actually result in poorer patient outcomes. Because our workflow is also automated, it doesn't require pathologists to manually analyze slides for various prognostic factors. But of course, this doesn't mean that we would exclude the need for a pathologist. The pathologist still needs to make the accurate diagnosis, and then we can run the images through the workflow to obtain a little bit more prognostic information. And lastly, the workflow being quantitative means that it's not subject to any operator bias or semi-quantitative manual assessments, which are how a lot of research is currently done now in oral pathology by sort of grading in the low, medium, high sort of category. And finally, I'll just touch on some of the potential applications of the workflow. Like I mentioned earlier, TILs have been identified as a prognostic feature in many different cancer types. It was kind of first popularized in breast cancers. So what we did was to try and obtain some images from a public database, and we ran, and these are all of breast cancer, and we ran our workflow through on these images, and you can see how it does quite a good job at segmenting and quantifying the number of TILs. So I think it can potentially be used as a research tool to quantify TILs in many different other cancer types to investigate their prognostic significance. And finally, hopefully a little bit more interesting to the audience today is the fact that you can, because we're doing everything at a single cell level, segmenting each individual cell and then classifying them, we can obtain spatial maps and upload this into simulation software like CompuCell 3D. And this is actually what we did in last year's CompuCell summer school. But of course, I'm not an expert on, I'm not an expert on computational modeling, so I'm not gonna discuss this in too much detail, but I think this is potentially quite an interesting potential application of the workflow. All right, that's all I have. Thank you very much, and I'll be happy to take some questions at the end.
Great, thank you very much. Covered a lot of material in a very compact way. I appreciate it. And so our next talk is from Yuefan Deng from Stony Brook University, otherwise known as SUNY Stony Brook. Talking about multi-scale and machine learning algorithms for modeling large blood clots. So you've had other Stony Brook people talking about blood dysfunction in relation to infection. So I will turn it over to you.
Thank you for inviting me. And I'm actually currently on sabbatical at NYU Abu Dhabi. You can see my background. I'm 8 hours ahead of you for people in New York area. And that's why I missed a lot of good talks. It's now almost half an hour from midnight. This is a cherry picking of slides from hours-long seminars. So it can be disorganized. Let me just to give you what we have been doing over the last almost 10 years, collaborating with people in biomedical engineering, as well as in cardiology. We are in applied mathematics, so try to make math useful, hopeful. And the thrombosis is our motivate the research a little bit. And total heart attack and stroke cause worldwide annual almost 25 to 30 million people death. And there's other blood issues related. So diabetes cause almost 6.7 million deaths each year. I just checked as of today, COVID-19 caused 6.18 million deaths. It doesn't mean COVID-19 is not lethal, but heart attack and stroke was even more. as you can see, there are multiple issues resulting from a platelet a clotting, a blood clotting resulting from platelet aggregation. And it feels like a blood clotting is always bad. Turns out it's not always bad, and sometimes it's actually good. When you do have a cut, you want that platelet to raise over to block the bleeding. And this is outside, you may have some other ways to do. If you have, one has internal bleeding and platelet aggregation or coagulation is actually very important, very useful. Therefore, there's two sides of the issue. And what we are doing here is to study this little particle, this little cell called platelet. It has a lifetime approximately a week to 10 days. And each platelet has approximately 1 trillion atoms and is a biscuit size. It looks like a little a biscuit and about size of about 5 micron. And if you, I don't know if you can see my mouse, the cookie-like a character here is the good one, and the one on the right, getting all these spikes is activated platelets, and the growth spikes in the right place and the right point for the right number of them. We just don't know why. We're studying why. And those platelets, this is the right-hand side, what I'm looking at is the activated platelets. Those activated platelets tend to penetrate each other and causing clotting. Thousands, tens of thousands get together to cause a blood clot. As you can see, there's a little blood drop in the lower left corner of your screen is a 1 drop of blood. Is approximately 50 microliters and has 7 to about 22 million platelets. So as you can see, the intensity of a problem, and obviously platelets generated from bone marrow. And during those approximately a week to 10 days of lifetime, it can cause life and death issues. All right, the study of a platelet going from atomic to cell level covers a lot of space and time scales. And approximately from atomic to a cell is in 1 dimension, a space dimension is approximately 6 decades. And in time dimension, you can get up to almost 9 decades. So that's a very serious problem. And there's a serious problem in terms of computing. Obviously, the real serious simulation has been for the last almost 20 years. And people are using very simplified models to calculate the platelet interactions. Unfortunately, they're just too simple to study the real dynamics. We have been trying to use supercomputers, using machine learning, using a multi-scale to study from atomic level. And obviously, as I just mentioned, each platelet has almost 1 trillion atoms. You can't treat every atom equally. And then we need to have a multi-scale. And this is the whole story behind what we have been doing with generations of graduate students working very hard on the details. All right. So the issues we are studying, there are 3 of them at least. Number 1 is an activation of a platelet, and a platelet activated. And as I mentioned, a good platelet is a very smooth and flowing in the blood, causing no issues. And activated is the growth spikes, and those spikes will penetrate and then tend to allow aggregation. So the second issue is to study is a platelet aggregation. And then there's another issue is a platelet get adhere to the surfaces And then this is triple A, I would call adhesion, activation, active, should be the other way, activation, adhesion, and aggregation. Those are what we're studying. I simplified the problem into this matrix. And the first column, as you can see, is just a single platelet. And the second column is 2 platelets. And then the next one is generalized into n platelets and bigger than 2. Yeah, mathematicians like to always generalize. And going from a single platelet, we have phenomena we can study. Number one, how this little platelet is flowing inside the blood vessels, and basically it's flipping around. And the second one is the growth spikes. That growing spike process is academically it's called activation. And then there's one adhesion. This is for a single platelet. You got 3 types of phenomena to study. And for 2 platelets, and then there's one, they tend to aggregate in a flow, a free flow, yeah. And then another one is get recruited. One platelet was already adhered to the surface of the blood vessel, and then another one is get recruited. So this is a 2 platelet. There's not too much we can play with. There's a 2 phenomena, and then there's a 3. You get a bunch of them in the free flow, and then there's again adhesion, and then finally you get a lot of them to get the aggregation and adhesion. It get pretty complicated, but this one slide shows what we have been busy for. Each of this picture will cost a few PhDs a life. And let me quickly show, just in case I don't have time, I show some later things earlier. And number one is to study the details of the dynamics of a few platelets moving around a few other platelets. In this picture, this is actually a real run. The picture here on the left, the movie, as you can see, the 3 blue guys are 3 platelets that get absorbed on the surface of a blood vessel. And by the way, a blood vessel is rectangle. Nobody has such a blood vessel. It's just for simplification of a calculation. Someday we'll have to make it more real. And now these the 3 platelets are patterned around, and obviously it's much faster than what we demonstrated here. And then this is we got 3 plus 3, and then there's another one. We get 4 as the base, and got 3 coming in. And as you can imagine, there are a bunch of possibilities. Possibility number 1 is the new coming platelets will get aggregated to the existing aggregates. And that's number 1 possibility. Number 2 possibility is, as you can see, they pass through without any big impact. Number 3 is they actually come to the existing aggregates and chip away existing aggregation. So this is what we wanted to study. Under what flow conditions each of those will occur. So this is still research in progress, and we get some results, and those are the pictures. And the next one is a little bit reflecting our title of the talk is a big aggregate. And we study aggregation of 250 platelets. Remember, each blood clot is something a few thousand. We're not approaching the real thing yet, but it's getting close. We mimic this, the long thing is a section of blood vessel. And this here is we made a stenosis with a few, I believe 70 platelets for the stenosis, and get narrow channel, because this is a reasonably real. It's like a cholesterol. You get deposit on the vessels, yeah, and you get narrow channels. And we wanted to see how the platelets will flow through. And again, we change the flow conditions to see how they actually interact, how this aggregates are building up or getting actually a little bit reduced. So it is a lot of parameters to go through. Let me show you a little, this is a movie we obtained after a few months of a calculation on a huge computer on a State University of New York, and IBM generously offered us access. And if you look this very carefully, I did a little math here, and this is about 1 minute flowing inside inside this guy, and it took us 2 months to use computer to simulate such a phenomenon. If you look at this, we need to make a digital twin of this blood flowing inside a vessel. We still need to speed up the calculation compared to that fellow there almost 1 million times. It's not likely to happen overnight. It may happen in our lifetime to speed up this calculation by a combination, a collective efforts, algorithms and the parameters, selection or equation, and as well as supercomputing. Now let's get to the details of the study. We got 4 different issues. Number 1 is building the model itself, and I think I have last only 5 minutes. The building is a molecular dynamics in multi-scales, and all the way from this core screening MD and core screening MD with DPD and all the way to CFD. So it's a mouthful to get all those equations to study different aspects. Now with that, we need to, those equations have a lot of parameters. Where do we get parameters? We need to use machine learning to extract such parameters. That took a long time, and I'm not going to spend time, quality time to get to these bloody details in here, geometrical and physiological parameters. And we do some, a lot of experiments by our biomedical colleagues. And then we use machine learning to extract the parameters to feed into the models. And then this is somehow the parameters we extract. And this is a demonstration of a real thing. You're seeing the blood, the platelets in the microchannel flowing around and then aggregate. And now let me flip through those slides for our learning of those parameters. And the next one is issue number 3. Remember, we said there's a multi-scale. Multi-scales at different times of the simulation at a different space. We need to use the right discretization. And the right discretization actually is in both space and time, at space and time. Although we are just solving ODEs because it's a molecular dynamics, and essentially it's a molecular dynamics. So what we do here is cut this into multiple time scales in different regions at different times. This is one of our former students, a PhD, when finished, my God, almost 7 years ago. This is one. If you look at this, it's almost like the clock needles. You know, this is the hour needle, hour hands, and then there's the minute hands, and then second hands. We cut it into pieces. So we need to assign which piece of a calculation at what time using what a resolution. Turns out for a long time we did this more or less manually by intuition, and later now we use a machine learning to decide. And this is a picture basically showing what I just said. And there's 3 resolutions for your calculation, okay? This horizontal is just some space and time, and vertical is our resolution in time. And there's one very foolish one is using single time scale, the red line. You resolve everything in terms of physics, science. By the way, the green line is the behavior or the resolution you need for the physics or the physiology. And obviously, in order to calculate correctly in your MD, you need to use the shortest or the smallest time scale. So this is the red one. You obviously waste a lot of time to resolve things you don't need to resolve. Yeah, and then you get a field scale. There's a goldish line. You use this time scale. You actually save a little bit and somewhat in the middle. And then you'll get this purple line. Just get as close to the needed a resolution of science as possible. So when we simulate, I would say this is like acting. You're acting like you play Lincoln. You want to be Lincoln, no more, no less. Simulation is exactly the same thing. I resolve the physics. I resolve exactly what's needed in the simulation in terms of time scale, no more, no less than the actual scale. Obviously, it's very hard to figure out when and where to use what scale. And this is what machine learning is about. This slide will take 5 minutes to explain. Let me skip this. And then this is the discretization conceptual level. Basically, we determine the spatial scale, which is actually slightly easier. And then there's a temporal scale. What is the thing we're doing? Conceptually, is actually the objective function here. We wanted to find an argument of this function. This is the characteristic scale of the problem. And this is what the in silico scale you want to attempt. So the phi characteristic is fixed, is given by God, is the problem itself. And this is what we, in silico is what we decide. And then we wanted to have the minimization of the differences to enable the argument will be the selection of this. Okay, those are the machine learning. We have to make one MD first to get a parameter to know the behavior and then learn the parameters. And then we use the inference and during the calculation of MD. You actually record for the last, say, 1,000 steps of a run, and you use that result to predict the time scale for the next, I call omega steps. We use a constant. And then after the omega steps, we do another learning and keep doing that. That's a learning. This is a pretty recent a result. It lasts about 3-4 years of calculations. I will flip this a little bit quicker, and then I will show you the ones implemented on a supercomputer. I think I have minus some minutes. And this is done on the, as I mentioned, and it's very big, very fast. I think it's the fastest computer in the state of New York, and we get approximately 20 petaflops, and obviously this machine is shared. We get not the whole thing, and probably on the average we get a single-digit petaflop performance. So this is the team. I thank. Danny Bluestein is my colleague in at Stony Brook in biomedical engineering, and he is the science side, and this is the rest of the team. Surprise, surprise, we can actually conduct research thousands of miles separating us. Thank you.
Thank you very much. Thank you both for getting through a lot of material quickly. 2 good talks emphasizing machine learning approaches Open for questions.
This is John.
Go ahead.
Maybe one of my typically naive questions for the first presenter. That first of all, we have to assume that the 26 patients, 2 groups, were treated the same way, and 26 had a bad outcome and 26 had favorable outcome. But I'm assuming they all got the same treatment.
No, so they didn't get the same treatment, but generally for HPV positive oropharynx cancers, the first line treatment is always radiotherapy. If they tend to be a bit higher stage or a larger tumor, then we might give chemotherapy on top of that as well. But most of them are primarily treated by radiotherapy. I know the patient numbers are not really large, but actually 29 patients is all we had from a period of 12 years for patients who did poorly, just because they are quite a small subset of the whole cohort. Yeah. So we try to sort of.
Yeah, I mean,
when we did this. Yeah.
I don't know anywhere in the world you could ever come up with patients to work with where you could say that they got the same treatment, but then, just picking at one spot off of one of your slides where you had a list of differences in the characterization of the tumor. And one of the differences was the unfavorable outcome people's tumors had homogeneous cell sizes, that the size of the cells was not uniform, as opposed to the survivors whose tumors tended to have cells that were of similar size at least. And which just poses the question to me, did they have 2 different diseases that whatever the genetic manifestation of my tumor was one kind of a cancer that was uniform cell, and the other group had a totally different expression of their genetics that produced a cancer that had nothing to do with the one I had. And I just don't know how you ever are going to be able to sort all that stuff out. I so admire the people who are trying to discover what the differences are, but then we got to understand why the 2 were different to know what to do about it, if anything. Thank you. I mean, both presentations were really good.
I think you're absolutely right, and I think there is some debate going on as to whether or not maybe some of these HPV positive cancer patients are they really entirely due to the virus itself, or predominantly due to the virus, or are there several other sort of genetic mutations that are maybe a bit more similar to the HPV negative cancers? So that there is always that sort of a debate, and you're absolutely right. They may just be sort of a little bit different in that sense. Yeah.
Other questions? I have.
Thank you.
I may ask follow-up questions for Jonas. I've got other questions for our second speaker, but let me start for Jonas. And I was going to ask, when you did your graded analysis of predictivity for your neural network, I saw that your overall predictivity was 78%, which is pretty good. But if you look at the failures, they're not clustered near the boundary. You have some extreme failures where the misprediction is dramatic. And I was wondering, if you go back and actually look at the individual slides, are there features or aspects that you can identify that might explain why you're doing that misprediction on those particular examples?
Yeah, I think some of them actually, when we went back to look at some of those specific classifications, you end up tending to find that some of them have although they are from a patient with a poor outcome, they actually had a lot of features of good outcome patients, like high numbers of TILs. So they had a good immune response to cancer, but for whatever reason, perhaps beyond the variables that we measured, they didn't make it for whatever reason. Yeah. So yeah, there's always that sort of heterogeneity in terms of these patients.
But there was no pattern of failure. In other words, there were no features your brain extracted that were missing from the feature set you were using for your classifiers.
I think we only included features of the biopsies that we measured, but we actually didn't include any of the sort of clinical features, like maybe their smoking status, which maybe could have played some of a bit of a role, or their age, for example. Yeah, so perhaps in the future, if we include some of those features, the model can get better as well. Yeah.
Thank you. Other questions for our speakers? I have one for our second speaker, if nobody else is going to come back to it. I actually, you were very good about skipping over some slides, but I would like you to come back. I'm very interested in this question of inverse problems of parameter identification and how to use ML to do that. So would you be willing to walk us through a little bit more, since we have a few minutes, would you be willing to walk us through a little bit more detail on how you were doing that very complex problem?
The parameter selection is at this point somewhat not entirely machine learning. Is somewhat as a inverse problem in this case, and we did experiments, and from those experiments you match the calculated results by adjusting the parameters. And we did a lot of tests, and then we got the right results for that. And there was one student who did this work. I said during her time was human learning. She basically runs a calculation, and the result doesn't match the experimental result. Then we go back. Now we do the learning process. And if through learning, we get the right parameters, and then we test. And then I unfortunately don't have a slide for this. This is another student's work. I didn't prepare for this portion. Yeah, basically is just keep trying the calculated in MD, very expensive, and then match with experimental result. Yes, that's the parameter decision part. Yes.
So if I can continue on that problem, you mentioned that when you did the experiment and then the inverse problem, you could get an estimation of the parameters in about a decent amount of time. I mean, reasonable. But then when you try only to do the machine learning route, that it took much more, and it was much more expensive to run. Do you anticipate in the future that the technique will be developed such that the machine learning on its own will be able to do this in a timely manner? Or do you see the future where it will be always needed that you have a certain set of experimental data even after the machine learning to optimize the process?
A very good question. Is looks like for the next 10 years, we'll probably have a combination of human and machine learning together to do this determination of physical and geometrical parameters. And I just realized there are some details in determining even the geometry. The calculation, because you need to, the platelets will have to take images, and then from image we do perform a segmentation. From the segmentation, we determine the size and the shapes from those, and we feed this into the calculation. Since otherwise I just treat it as an ellipsoid, but it's not a ellipsoid. So we determine the average shapes, and this is one of the learning. Turns out the geometrical portion was a little bit more systematic, because you just take images and then also remember it's a 3D. And our image is 2D, we have to flip them around and calculate. It was pretty expensive, and it took a lot of efforts. And then this machine parameter determination is, we guessed the force law with with a lot of accuracy already. And then there is some parameters, if I show the slide, and then there's the intensity parameters, and then there's a form factor parameters, so not too many. So it's a reasonable, we determine the physiological parameters entering the MD calculation. They are pretty complicated, pretty expensive, and there's a lot of intervention. There is a somewhat after the fact, and then you calculate results and the match the experiment result. So then we claim it works. Still, I must tell people not to trust us so much, because the calculations are too complicated, and we need to validate by some of the experimental results, and we keep adjusting. For example, the shear stress, to see how they actually will aggregate, and the aggregation dynamics as the input of the flow. And then there's a viscosity of a blood, and then there's the shear stress, and then how they respond. It's like two independent parameters with one dependent parameter, which is the dynamics of aggregation in this particular setting. I was trying to concentrate on resolving, understanding one problem completely, not to just study the whole thing. So we get a few independent parameters, variables 2 to 3, and then get 1 or 2 dependent variables. So the dimension is reasonably small. And then if they have a total confirmation, then we think it's reasonably started as a more reliable.
I had
Lorenzo, go
one.
ahead.
One for Yuefan. Well, beside the amazing work, really interesting. I was wondering, just as a matter of consideration, if you show your picture in a channel, and I think it mimics more your experimenting fluidic experimental system. Have you considered, or are you trying to extrapolate to vessels that are bigger? So the aspect ratio between the platelets and the actual caliber of the vessel is different, such in big vessel, I don't know, the aorta, etc. And then also the geometry of the actual channel. So I know that this will include even more complexity, but if you're thinking to go into the direction or already done.
There's two issues here. Number one is in terms of traditional laboratory experiments. And unfortunately, those experiments have a lot of issues. The issues is that they don't have a dynamic details, and our calculation will show the dynamic details. Yeah, if it's correct. And the second one, Lorenzo, like you said, the geometry of blood vessels. And currently, we just get a steel rectangular vessels. It's a little bit embarrassing, but the geometry makes it easier. And in the future, we are actually setting up that make it, number one is a tube. Number two is a flexible. So it's down the road, we'll get more and more real. But at this point, we don't have it. And what we have is just make a rectangular vessel. I keep telling people, our students, is this is some some spaceman, not the alien, not a human being, yeah, or any other things. Yes, there are some complementary properties in here. What we use simulation compared to the regular laboratory experiments, and there are some things we learn in this process that's actually are useful. And what is to predict from the geometrical shapes of platelets the potential of aggregation or clotting. And if you see this is a machine learning process which you told me not to tell. This is as you can see, for young kids, their platelets are much smoother. And when people whose platelets got beaten up during their lifetime, and then we get a different distribution of their shapes. From those distribution with machine learning, we can actually compare with their potential or their prospect of being aggregate or clot. So that's the side project. We were learning the geometries of the platelets, and we use that to make this correlation between the probability of platelets aggregation and the platelet shapes. Yeah.
Thank you.
Okay, other questions? I'll ask a question again, coming up back on the ML. You mentioned that you're using adaptive time stepping and adaptive spatial resolution. Is the time step uniform over the whole simulation? That you adjust the scale that, or is it localized? Is it local time step?
Well, is number one is also localized, but localized is domain by domain. Yeah, it's not entirely accurate to individual particles as we wished, which is not practical. And you get a blob. Here is the flow. Here is the inner part of a platelet. Here is a membrane platelet. You use different time scales, and this is in terms of space. And then in terms of the time, we can also, since it's MD, yeah, it's a function of time, and we use at different times and get different delta T's. So this paper, which is recently published in JCP, Journal of Computational Physics, is by learning the past dynamics for 6 or 7 dynamical parameters from which we predict the delta T at the right region at the right time. And we predict 2 things. Number one is the actual resolution we will use during the next, say, 500 steps. And we not only predict the time, we also predict for this 500 steps. And we use that a calculation. This saves time, but not by a lot, because you need to learn. And you need to record all this time, and then you use this to do calculation. We did a very careful analysis, and those are the slides I didn't show. We get an accuracy approximately 90%, 97% compared to the one single resolution, single lowest delta T.
Right.
Yeah.
Is it complicated to maintain synchronization when you have different time steps in all of your code?
It is. It's just a nightmare for this to work. And yes, it is. And then we get to a certain time, we just match them up and synchronize, and then start again. Yeah.
Now the spatial models, if it's MD, it's not a meshed model. So if, on the other hand, the solid parts of it maybe are meshed, where is this? How is the spatial resolution determined? And what does it require to change spatial resolution?
Particle sizes, yeah. What kind of particles you're going to treat in? Some is not, you're using a single atom, and there's a collection.
Okay.
Yeah, that's what I call by space. And
So you are remeshing by taking one particle and replacing it by multiple particles, or vice versa, to get your spatial
exactly
resolution.
right. Exactly.
So how do you
right.
do the remeshing when you do your AI system says you need to do finer spatial resolution, and then you do a remeshing where you replace the particles by multiple particles to do, or you do a decimation where you.
No, that would be probably too expensive. And what we did is we recognize this particle belongs to which portion of the physiology. Is it a membrane, or is the inner plasma of the platelet, or is the flow, or is the particles near the surfaces? So we treat them. They have their identities, particles. They are in different regions. We treat them as different types of particles.
So it's not a dynamic remeshing like you do for diffusion, where you say you measure the local gradient and you remesh to keep the gradient resolution the same. So you're not doing a dynamic remesh.
No, we're not doing that. Fortunately, they don't change shapes like a plasma. The platelet tends to be intact for a long time. And they are the membrane particles. They stay as membrane particles. They cannot change too much. But you just have to recognize them when you do the calculation. Exactly, we're not doing that. In a more mathematical picture is you need to first get a cluster. They can remarry to form another cluster, and then you use that calculation. I'm trying to push people to do that. Doesn't look like we'll have any results in the near future. What we're doing now is somewhat cheating. We recognize which they belong. We know they have to have a certain range of interaction skills. And for example, for flow particles, we can do very easily. For particles near the platelets, and then we have to use one spatial scale. And the particles on the membrane, we use another scale, yeah. And then of course, time is based on there's 5 or 6 different parameters we collect, and then we predict. Time is predicted for a given domain, we give a time, yeah. And of course, like you said, different domains will have to be synchronized at the end. We do synchronize them, yeah. There is a reason how we synchronize it. The details is probably a little boring, yeah.
Okay, thank you. I guess I was going to come back to the first talk, and it was impressive that you're able to do all the segmentation and identification using standard packages. And I was wondering if you have where you have the most problems using cell profiler or the segmentation. Do you have cells that you can't segment? What happens? What you do? How do you deal with failures in those kinds of workflows?
Yeah. So there are definitely lots of cell types that we can't really segment. So one good example are like macrophages, which tend to sort of have a very pale cytoplasm, look sort of foamy, and they're really hard to actually identify without any additional stains. So for those, because they're so palely stained, they don't even really tend to be identified or segmented as a cell. So we just kind of ignore them. And I think in most studies as well, they kind of we're not too sure what role they play, so we kind of just ignore them as well. So another issue is that we tend to get is when we have sort of tissue debris from crushing of the biopsy, either during preparation or during surgery, you get a lot of debris material leaking out, and we classify them out during the round of cell profiler analysts. by just sort of classifying them as debris and then ignoring them in the downstream workflow. Yeah. And I think the hardest part was really the stain variation. There are quite a lot of sort of either models out there looking at dealing with this stain variation. We did try some of these published models, but it just didn't really work very well. And also sort of bearing in mind, we are using a lot of images that are retrospective. So they've been sitting in the archive since 2005, and we're just pulling them out now. So a lot of them are very pale, sort of faded over the years. And we had to try and develop a model that was able to be robust enough to deal with that variation. Yeah.
So I'm quite impressed. I think that the fact that you can come up with a workflow that works for just random HCA slides is impressive. And I noticed, I was just looking at some images and realizing that I was having trouble in some of the images distinguishing nuclei from nucleoli because of the way the images were taken. So I thought that the fact that you could do that kind of focus on those distinctions was interesting.
Oh, thank you.
Wonderful. Are there other questions? I think we've had a good discussion. Any final questions for our speakers? Well, we better let both of our speakers are in Eastern time zones from us, so it's late for both of them. So I want to thank our speakers again for coming and giving us two very interesting talks looking at the intersection of machine learning and these kinds of problems. And I thank you again. I hope to hear some updates at some point about your progress on both projects. And then I'll say again, thank you to everyone for joining us today. Look forward to seeing you again next week.
Thank you.
Thank you. Thank you.
Thank you. Bye.